Hello, welcome to the Dotcast, the famous dog podcast where we interview some of the most famous scientists. Today, we have one of our favorites here. Mr. Hubble, could you tell us a little bit about who you are and your project?
Wow, there, Mr. Goliath. Thank you so much for the warm introduction. It's a pleasure to be here with you today. So my name is Edwin Hubble, and I am an astronomer who set out to prove that spiral nebulae were separate star systems outside of our galaxy and not gas clouds in front of it. I was able to accomplish this using the Hooker telescope to study a Cepheid star, specifically named V1, in what we now know to be the Andromeda galaxy. Cepheids are a type of star that pulsate, and I want you to imagine that you have an observable star, right? But it's flickering an unknown distance away. And its brightness, it's not necessarily constant, but it changes in a predictable pattern over a short period of time. So, building on the groundwork laid out by Henrietta Leavitt, I timed V1's pulsation period and used her relation to calculate the true luminosity. From there, I compared that calculated luminosity to how faint the star appeared to us here on Earth, which allowed me to calculate just how far away it really was and thus determine its location in relation to the Milky Way galaxy, which pretty cool stuff if you think about.
Wow, that's truly amazing work there, Mr. Hubble. So, what was really the point and the goal with this project here?
Well, as you know, Dr. Herbert Curtis was part of the great debate against my colleague, Dr. Harlow Shapley, who was, if I'm being candid, not too fond of my ideas. The main argument I was attempting to prove was that the Andromeda was not just a cloud of gas within our own galaxy, but was in fact a separate galaxy entirely. And if I could show that using V1 as my evidence, it could settle that debate once and for all.
Now, could you tell us a little bit about behind the scenes or where really was this project taking place?
Of course. So the project began shortly after I arrived in California back in 1919 at the Mount Wilson Observatory, and it was carried out using the 100-inch Hooker telescope.
Wow, amazing. Yeah, California, that's gotta be so fun. But what about what other things were going on in the world at that time? You know, we have your discoveries, but I think a couple of other things were going on as well. Can you tell us a little bit more about that?
Yeah. So you have Dr. Arthur Compton performing the Compton scattering experiment, which where he was able to demonstrate that X-rays change in wavelength when scattering electrons. That proved that light photons carry momentum like particles. And separately, in the medical world, you do have Doctors Frederick Banting, Charles Best, and John Nicolau developing insulin and actually injecting it to treat the first diabetic patient.
Wow, yeah, insulin, very very important, and Mr. Compton's work was really important as well. So anyone else that you'd like to shout out as part of this project here that you worked on?
Yeah, so I do have an assistant with me on this project. His name is Mr. Milton Humerson. He was responsible for taking long exposure photographs and spectrograms using the Hooker telescope that we have on site. And he also assisted me in observing and collecting data from the spectrograms to measure the redshift of the nebulae that we are observing. There are a couple of other people who didn't necessarily work alongside us, but whose work that came before us helped us tremendously in helping us achieve this goal. The first person that I would like to speak about is Ms. Henrietta Leavitt, whose work on the variable stars, specifically the Cepheids in the small magnetic cloud, laid out the groundwork for us to be able to measure distances using the luminosity period of these stars. Her work, which is now known as Leavitt's Law, states that cipher variable stars have longer cycles of dimming and brightening, and and that its pulsation period reveals its true brightness. So the second person that I would like to talk about is Mr. Vestos Slifer and how the work that he laid out for us was very important in helping us translate the data that we were absorbing on the spectrograms that we were collecting. Mr. Slifer's work states that, similar to the Doppler effect using sound waves, that light waves will expand and move towards the red light end of the spectrum known as redshift. When they're moving closer to you, they will contract and get smaller, moving towards the blue light end of the spectrum. So then he took the light from these spiral nebulae, laid it across the spectrum, and he looked for dark lines, which is he called absorption lines. Would and those relate to known elements. From there, he would measure the change of these lines from their usual position, and using that data, he could tell whether or not an object was moving closer or away from you.
All right. Yep, Mr. Hubble. And how can you tell us a little bit more about how you played a part in this role and exactly what your contributions were during this project?
Right. Yeah, I was the main contributor of this project. As I previously mentioned, I had an assistant, Mr. Humerson, whose primary role was to just collect data, but I was the one responsible for translating what we were observing. It all started with finding a couple of variable stars, one specifically that I named V1 in the Andromeda Nebulae. From there, we were able to focus on a couple and measure their redshift using spectrograms as well as determining the luminosity period. Um, I used Mr. Schleifler's work to measure the velocity, and from that, I was able to create a relationship between the both, which is now known as Hubble's law. That states that galaxies are moving away from Earth, specifically at speeds directly proportional to their distance.
Wow, Hubble's law, Mr. Hubble. That's gonna leave a significant impact on your legacy there. Well, well, thank you so much for sharing that. And a couple more things here before I let you go. What could you say was the ripple effect that your project had on the physics community?
Wow, Mr. Goliath, thank you. Thank you for your kind words. It truly means a lot. Um, yeah, so a couple of things to mention here. So the physics community, it kind of helped us determine and change the idea of what we consider to be the observable galaxy. The variable cepheids that we observed, we used the redshift data to help calculate the distance at which they were away from us, in this case, moving away from us. And we determined that they were approximately 900 light years away. And at the time, we believed the Milky Way galaxy to only be about 100,000 light years across. So, in conclusion, how could this gas cloud that we see in this telescope even be in our galaxy if it's wider than our galaxy? It forced us to confront the idea that other galaxies may exist, that it's not just the Milky Way galaxy, and thus it helped expand our idea of the observable galaxy, of this known scale of the universe in itself. Um, and it forced Albert Einstein to abandon his idea or his theory of the static um, universe model, which it helped to move on to other things, other greater contributions.
Oh, yep. I bet Mr. Einstein was not happy about that. But amazing work there. Yeah, expanding the scale known of the universe. That's really amazing work, Mr. Hubble. All right, last question for you. We're gonna finish on a high note. I'd just like to ask, what was the most surprising moment during your research here?
To me, the most surprising or like moment of all that I felt was um, after I calculated and double checked my calculations. It's kind of remarkable to think about something being 900 light years away from you, and to know that this is the closest galaxy to us. It's kind of a very a weird feeling of feeling very human and insignificant in the grand scheme of things. To know that there are things larger than us, and that the universe isn't isn't just stable. It's still growing. It's still expanding. That where humanity has gone is not where we're always meant to be. We're traveling across this universe at speeds at which we can't even imagine. can't comprehend. And it feels like we're stationary the whole time. To me, knowing that the universe is still expanding was the most remarkable moment of this research for sure.
Oh, wow, Mr. Hubble. Well, thank you so much for taking the time out of your busy day to talk with us today, and all the fellow scientists and dog lovers out there really appreciate it. All right, thank you for your time, and hope you have a good one. Bye-bye.